Okay, welcome everyone. So today what we're going to be talking about is the Born Haber cycle, and as well as talking about lattice energy. So let's actually just start off first by talking about what is this lattice energy. So I don't know if you remember what it is, but it's the energy something. Let's see if we can remember the first word. The energy required, I like it, to do what? To separate or break how much? 1 mole of an ionic substance or an ionic solid, specifically an ionic solid, into what? It's gaseous ions. That's perfect. That's awesome. Okay. So when we're talking about this lattice energy, the way that this has been calculated is you actually can take different steps. We typically see a reaction as reactants, arrow, products. But in reality, there are a whole bunch of different little things that are happening. And this Born Haber cycle actually takes us through a whole bunch of steps for forming one ionic solid, okay? And so what we do is we use the enthalpy of formation, actually the reverse of the enthalpy of formation. We use the atomization. If it's a diatomic molecule, that means that you actually separate the diatomic molecule into its atoms. We use ionization. Everybody knows what ionization is. What's that? The energy required to remove an electron, so we do the removing of an electron. But then on the other side, we actually have, it doesn't show it in this chart, but we've got the attraction or the addition of an electron. Does anybody remember what the addition of an electron is called? Electron affinity. Awesome. So then we have the addition of an electron. And then we actually end it with this lattice enthalpy. And so this lattice enthalpy, it shows here, is the negative of the lattice enthalpy because in this case, we're actually forming an ionic solid. But what did we say lattice energy was? It wasn't the making of an ionic solid, it was the separating of the ionic solid. So this is actually going to be the reverse of the lattice energy, and then you kind of close this back up again here. This full cycle is supposed to basically equal out to being 0, okay? The whole cycle from going around in a big circle ends up equaling 0. And so it says, what is the conceptual basis? Because enthalpy is a state property, it must have the same value at the beginning and the end of a complete cycle. Therefore, the sum of the enthalpy changes must be equal to 0. Okay, to use the cycle, what do? So it says that we typically start with the elements. Usually we have a metal and a non-metal, or a cation and an anion in the appropriate amounts to form the compound. And then we make these changes that it basically says. Okay, what they do is, if it's an endothermic process, then they draw the arrow going up. Guess why? Endothermic means energy is absorbed. And if it's exothermic, then what we do is we draw the arrow pointing down because that would be releasing energy. Okay? So this basically just goes through all the different steps. So it says to start with the elements and the proportions and atomize them. So that's basically step 1 is to atomize them. And we use the thermal chart. And so you'll see in just a second, we're going to go to this in a second here. Step 2 is you form the gaseous cations from the metal. So whatever the cations are, you're going to switch those atoms, whatever phase they're in, into their gaseous cations. What does that mean? Well, that means that you are going to ionize them. So in order to form a cation, that means that it's losing an electron. So you're going to use the ionization energy. The arrow always points upward for ionization energy. Why? Because ionization energy is always the energy required. Perfect. That's always going to be an arrow up because it's always required. Step 3 is you're going to form the gaseous anions. So the anions, what's an anion? It's an ion with a negative charge, which means it gained an electron. So you're going to form the anions. Now, this could be positive or it could be negative. I don't know if you remember this, but electron affinity could be either way. It could go in either direction, so it depends whether the arrow is going to go up or down in that situation. And then you would just still use your thermochemical chart to figure this out. Again, I'll show you how enthalpy for electron affinity, we can actually use the electron affinity chart. So I'll show you how that works. And then step 4 is you let the gases form the solid. Okay, you're going to form the solid. This says it's the reverse of the enthalpy change of the negative. It's the negative of the lattice energy. So instead of going, your solid is breaking up into gaseous ions, it's the gaseous ions forming the solid. So we'll just do the negative of it. And then you complete the cycle with the enthalpy of formation delta HF, which again you can get from your thermal chart. Okay, step 6 is calculate your delta HL, assuming that everything equals 0. Then you just sum everything going around and set it equal to 0. That's basically it. Okay, so you can see the chart here. Okay, so let's flip. What are we going to be doing? So this shows an example of one. This shows a sample one. This is not how a problem is going to be set for you, okay? Typically, the way that a problem is going to be set is similar to the bottom of the page. So let's take a look at this real quick. What they do is they give you a list of different reactions, okay? So these are more like intermediate steps, intermediate reactions in when we were doing those thermo manipulation problems. And what you do is you basically have to set it up so that it all ends up equaling the enthalpy of formation reaction, and then you're solving for X, okay? So similar to when we did, you add them all up and it equals a certain number. Well, and when we were doing in thermochem, we did this already, where instead, one of the steps is your X step, and so you're going to add them together but subtract from the total. So I'll show you how that ends up working, okay? All right, so if we take a look at this, it says using different charts. I just want to check to see where they're getting these values from, rough values of these, because these may be slightly different from what we have in our charts. Let's see where they ended up getting these values from, okay? So what they're showing us here is they're showing potassium as a solid, and potassium is switching to a gas, okay? So we're going to take a look we're going to look at potassium switching from a solid to a gas, which means we're probably going to need our thermo chart. So we're going to go over to the potassium section on our thermo chart, and I'm taking a look down on the bottom, and I see, I know this is really small, but potassium is a solid. We all know the value from the thermo chart. Potassium as a solid is in its natural state, so what would the value be? 0. But potassium as a gas is 89.99. So if we take a look back here, we can see that this says a positive 89 kilojoules per mole. Okay, so that's where they got that number from. You just do products minus reactants, okay? And that's how they got that number. This one says take potassium as a gas, and it still stays as potassium as a gas, so that didn't change. So what changed? Well, we have 1/2 Cl2 gas, and we're changing it to Cl gas, okay? Notice here, what's 1/2 times 2? 1. So is this balanced? Yes. That's 1 Cl, and that's actually equal to 1 Cl, because 1/2 times 2 is equal to 1. So that's fine. Well, what do you know about Cl2 gas? What's the value on your thermo chart? 0. 0. So let's take a look. Let's take a look at our thermo chart. So here is our chlorine section, and yes, Cl2 gas is equal to 0. Cl gas is equal to 121.7. Okay, so if we come back, this one says 122 kilojoules per mole. So that's our 121.7. Okay, so that's that step right there. All right, the next step is, well, what happens? Well, I'm going to take a look from here to see what changed. And I can see that my Cl gas is still Cl gas, so that didn't change. But what happened to potassium? It lost an electron. This actually became K plus electron. If I pull this reaction out and I write K gas yields K plus an electron, what does that look like? Ionization energy. Yes. What's electron affinity? Gaining an electron. What's ionization energy? Removing an electron. We can see that an electron was removed. So there it is. It's being removed. If it's being added in, it would be on the left side. Okay? So where am I supposed to get this number from? You're not going to find it on the thermal chart. Where do we need to look? The ionization energy chart. So we're going to take a look at our ionization energy chart. And what am I looking for on here? Potassium. Perfect. So I'm going to find potassium. And it's the first ionization energy right there. Okay? If there were a substance that were losing 2 electrons, then what you would do is you would actually add up both of these numbers together. So in this case, it's just potassium losing 1 electron, so I'm just going to do this number. You don't multiply it by 2, because remember, the second electron that comes off always requires more energy. Sometimes there's a huge jump, like there is for potassium. Why is that jump there? Do you remember why this jump is here? Why it goes from 418 all the way to 3,000 for the second electron? Yes, because it is stable like a noble gas is. It has a full energy level at that point, or full sub-level at that point. So to remove that second electron from potassium, the first one's easy to remove. That second one, there's going to be a huge jump there. So you would actually have to add both numbers if you had 2. Okay, so let's come back to this. And that's where they got their 418 from. Okay, on the other side, what we have is, let's take a look at what happened. What happened to potassium? Stayed the same, nothing. What about chlorine? Oh, this electron right here actually is gained, and so now we have chlorine forming Cl minus. So it's kind of like this part here now becomes Cl minus. Well, if I pull that one out, it looks like an electron plus Cl gas yields Cl minus gas. What is this called? There we go, electron affinity. Perfect. Okay, electron affinity. So in this case here, now where do I need to look? Electron affinity chart. Okay, so if you flip your ionization energy chart over to the back, you'll see electron affinities. Are we looking for potassium? No. What are we looking for? Chlorine, because chlorine is the one that's gaining the electron. This one is actually set up like the periodic table. So we've got our metals on this side, and we have our nonmetals over on this side. So looking for chlorine, and what value does it say for chlorine? Negative 349. Okay. Now, once again, I'm going to tell you, if there were two of them, you actually would have to multiply it by 2. Okay, so if there were 2 electrons that were being added in, this you would actually need to multiply by 2. There isn't a second electron affinity value. They do it as the same. Okay, so if you are adding 2 electrons, you would just double that. All right, so that's our negative 349. So we can see right there, that's the negative 349. This part right here is X. Okay, we don't know this value. That's the lattice energy, and that's actually the purpose of doing this, is to figure out what the lattice energy is. Okay, we've got one more step that we didn't do. So over here you can see that we took our K plus and our Cl minus, and what do we turn it into? KCl solid. Okay, there's only one thing, there's only one step left. And this is actually our enthalpy of formation step, because what's happening is we are taking KCl solid and we are turning it into K solid plus 1/2 Cl2. Let's see if you remember this, because it's been a while. What is the definition of the enthalpy of formation? So it's the energy, remember it can go both ways, either gained or lost for the formation of 1 mole of a substance from its elements in their standard state, not gaseous ions, okay? And it's not an ionic solid, it can be any substance. Well, here we've got the reverse of the enthalpy of formation. So this is the making of KCl solid if we were to go back down this way, okay? So what we're doing is we're actually reversing it. So let's take a look. We're going to look for, well, what's this value from your thermo chart? 0. What's this value? 0. So what are we looking for? KCl solid. So let's take a look at our thermo chart. KCl solid says negative 435.9 is the value that this says. And they put on here, oh, they didn't put negative, they put positive. Why? Again, because it's reversed. They're doing that in the opposite direction, okay? Now, and then once you do that, all you would have to do is add up all of these numbers, but they all are supposed to actually equal the enthalpy of formation. That's the target equation, is this one. But when you do it this way, it's a full circle, all equal to 0. So if you're trying to solve for x, let's see, we're going to pause for just a moment here. Okay, so we'll pause the video. And all we're going to do is check to see if we end up getting a positive 717. So let's take a look and see. Okay, so we got the 717, and we want to make sure the answer is actually a positive 717. Lattice energy is always going to be large and positive. Why? Again, because it requires energy. So let's go over the definition for lattice energy one more time. Okay, so let's write this down. So what is lattice energy? So what do we say? We started off by saying it is the energy what? Required. Awesome. The energy required to do what? To break or separate. Very good. Break or separate. 1 mole. I like it. 1 mole of what? Of an ionic solid. Good. An ionic solid into what? Gaseous ions. Perfect. Okay. So again, this number is always large and positive. All right. So what I'm going to tell you is there's going to be we're going to use a particular site here for these for practice, and so you're going to end up writing your answers down on paper. And this is the way that the problems look. So I'm going to take you to the site for just a second here. And so it'll say Born Haber cycles. And so then it says signs are very important. I will tell you that in here, they do want you to answer it as the negative. Okay, so they want you to put your answer in as a negative. So keep in mind, though, that lattice energy is always large and positive because it's the energy required to separate an ionic solid, and it always requires energy to separate those, okay? And what you do is you plug your answer into here, and then you click check answer, and then it will tell you whether you're right or wrong, and it'll keep a tally of like your results, okay? And you're just gonna have to do 5 of those. All right, so let's come back to this, and how does this work? So it says, number 1, rewrite all the equations to the right, leave out the enthalpy of formation line because that is gonna go below as your sum line. Number 2, write the reverse equation for lattice energy, also do that above the sum line. Number 3, you're gonna write your enthalpy of formation below the sum line as all the reactions should add up to equal what we call our target equation, what we always call the target. And then you're gonna manipulate your equation so that everything cancels out and you're just left with that final target, whatever is left in your target equation, and you're just gonna add them up, okay? So right over here, let's just rewrite these over to the right side, okay? So I'm going to do a sum line first. I'm going to do my sum line. And this is the sum line, okay? My sum line is actually this K solid plus 1/2 Cl2 gas yields KCl solid, okay? And this is equal to a negative 428 kilojoules, okay? Now remember, it helps to try to line up your arrows, all right? It helps to try to line up the arrows. So I'm going to put, since I wrote this one down here, I am going to, because this is my sum, that's actually my sum, so the enthalpy of formation is your sum. I'm going to add one other line in here, and you'll see what it is in just a second, okay? So based on this, having this as my target, what should I do to my top line? Should I do anything to my top line? Well, I'm taking a look at it, and I don't see anything that exists here in this line. I don't see anything yet, okay? So I'm going to hold off on that line. Let's take a look at the second line. Is there anything that exists here that exists in my target equation? Potassium solid. Okay, and what do I need to do to it? Check the coefficient and check the side it's on. 2 things. What do I do? Nothing. The coefficient's good and the side it's on is good, so I'm not going to do anything. I'm just going to rewrite it. So it's K solid. Line up your arrow. Okay, try to line up your arrows. And then my arrow, K gas. That way you're sure that everything is canceling out in the end. Oh, well, here's the K gas. And I haven't used the K gas anywhere else. It's nowhere else in this. So I could basically base this one off of this because it doesn't appear anywhere else. What do I want to happen to K gas? I want it to cancel out. So is it in the right place for it to cancel out? Yes. You want it on opposite sides. So you want the correct coefficient and you want it on opposite sides if you want it to cancel out. So actually this looks good because here's this here and here's this one here. I'm just going to keep it exactly the same. So potassium gas, then my arrow again, K plus gas plus my electron. Okay, and I did nothing to that one, so I'm just going to write these 2 values over on the side here. I'm going to write 410 kilojoules. I also did nothing to this line, and that was 78 kilojoules. Third line. Do I see anything in this equation that only appears in my target equation? Is there anything that only appears in my target equation? The Cl2. Okay, I like it. So the Cl2 here is right here, and does it appear anywhere else? Remember, we already pulled this over here, so that's the same thing. Does it appear anywhere else? No. Perfect. Okay, so let's use whatever you want to use. We can use a triangle for this Cl2 gas, and a triangle here. What do I need to do to it? Oh, divide it by 2. Okay, so let's divide this one by 2. Okay, so what am I going to get? I'm going to get 1/2 Cl2, and then on my arrow, then I get what? Cl gas, and what's the value now? 118? 118 kilojoules. Perfect. Positive or negative? Do I keep it positive? Did I flip it? No. So keep it positive. Okay. The next one, what about this line? Is there anything that you can find that only appears in my target? No. So what do I need to happen to this line? It needs to cancel out. Okay. So if it needs to cancel out, I can look at a different number of things. It doesn't really matter. I could even just look at the electron. The electron is pretty easy because I know my electrons have to cancel out. We could look at the Cl minus. We could look at anything, really. It doesn't really make a difference. So I see the Cl gases here, and I see the Cl gases here, and nowhere else. What should I do to that line then? Nothing. Perfect. Don't do anything to it. It's exactly the way it's supposed to be because I want it to cancel out. So I'm going to write Cl gas plus electron, then my arrow over here, Cl minus gas. And hopefully you have a little bit of space. I have a tiny bit of space for that last line. And this one we said stays the same, negative 342 kilojoules. In order to bind all of this, what I actually need to throw in is my lattice energy step. Okay, but it's going to be the reverse of the lattice energy step. Otherwise, it doesn't all add up. Okay, it's not going to all add up. I'm going to be off on what goes in here. Okay, you can either start with it so you don't forget, or you can end with it. It doesn't really matter. Okay, so what am I looking at? What would the reverse of lattice energy be? Start with the gaseous ions and turn it into the ionic solid. Perfect. So on this side, I'm actually going to have KCl solid. And on this side, I'm going to have K plus gas plus Cl minus gas. Do I know the value for this? No, that's what we're trying to find. So what are we going to call this? X. You are going to call that X. Okay? So now, all we're going to do is we are going to add up all of these numbers and set them equal to negative 428. And then we're going to end up solving for X. Let's just double check this before we do that to make sure that everything cancels out. Okay, so I'm just going to switch the color right here. And while you're doing your calculation, I'm going to show you how this all works out. So my potassium gas cancels out there and there. I can see that my potassium, my chlorine gas cancels out here and here. My one electron also cancels out there. My potassium ion, my cation, cancels out there. And my chloride ion cancels out there. And what I'm left with is potassium solid plus 1/2 Cl2 gas yields KCl solid, and that's exactly what I see in my target equation. Do you see that? Okay, so it's back. I love this because it's back to thermo and doing manipulation problems. All right, so let's pause here and see if we can get this added up together. So go ahead and calculate this. Okay, so when I add all of these numbers up together, I think it's easier to just add these up, do negative 428 minus the answer that you get for this, and you get that X is equal to negative 692. That is the answer that you are going to plug into here, although I want you, and you would just write negative 692, although I do want you to keep in mind that, again, lattice energy should always be large and positive. So even though that's the answer that you're entering into the system, it would be a large and positive answer, okay? And so basically, this is the piece that you're gonna need to know for the Born Haber cycle. You don't have to worry about all of the arrows up and the arrows down. Do you need to understand every single step and what's happening? In my opinion, I think that it's important to know how the cycle works, but coming to the math piece, this is all you're gonna really need to know, okay? And that's basically it for the Born Haber cycle. Have a great day, everyone.